Hi, my name is Chin Hody. In this video, I will talk about the Fourier growth of regular branching programs. This is joint work with Ted Pai and Salif Adam. So by now, it should be well known that every Boolean function has a Fourier expansion, which is a linear combination in the parity basis. The coefficients f hat s are called the Fourier coefficients of the function f, and these coefficients are indexed by subsets of the set of 1 through n. In this talk, we are going to study the Fourier L1 norm at different levels k, which is defined to be the sum of absolute values of the Fourier coefficients of f indexed by the set of size k. Naturally, we define the L1k of a family of Boolean functions to be the maximum L1k of all the functions in this family. Okay, so given a class of Boolean functions, we want to know if there is a B such that the L1k of this family is bounded by B to the k. It follows by the Cauchy-Schwarz inequality that one can always take B to be roughly square root of n. The notion of Fourier growth has found many applications in theoretical computer science. For example, it was first used by Mansour to give a learning algorithm for DNF formulas. And recently, the Fourier growth is used to give a separation of the classes BQP and the polynomial hierarchy. The Fourier growth is also closely connected to correlation bounds with the majority functions. And finally, this notion has a lot of applications in pseudo randomness, which is going to be the focus of this talk. So by now we know that many functions actually have bounded Fourier growth. By bounded Fourier growth, I mean that we can take B to be much less than square root of n. So for example, the Fourier growth of decision trees was studied to give separation of classical and quantum heuristic complexity. And the Fourier growth of constant depth circuits was studied to give learning algorithms for DNFs and more generally the class of AC0 circuits. And the Fourier growth of low degree GF2 polynomials is related to showing average case lower bound for AC0 circuits with parity case, which is a long-standing open problem. So there are other examples which include functions with bounded sensitivity and bounded functions and product functions. And in this talk, we are going to focus on the class of read-once branching programs. Okay. So let me now define what a read-once branching program is. This is a model of computation which is a central object for the study of space-bounded de-randomization, which is essentially the question of randomized log space versus log space. You can think of a read-once branching program as a layered graph with n plus 1 layers, where each layer contains at most W states, which is the width of the program. And each state in the program in the graph has two outgoing edges to the next layer, and each edge is labeled either 0 or 1. So we are given the start state of the program, and then we are going to read a bit each time, and then depending on the bit being 1 or 0, we update the state of the current state to a new state in the next program. So for example, this example computes is a branching program computing the sum of the first 4 bits, and it accepts if and only if the sum is not 0. So in the final layer of a branching program, we have a set of states, and the program is going to accept if you land in one of the accept states. And it's not hard to see that if you have an S bits of memory in a computation, then this corresponds to a width 2 to the S branching program. Exactly because there are 2 to the S many memory states. In this talk, we're going to focus on 2 restrictions of read-once branching program. So the first restriction is called the read-once regular branching program. And a regular program is just a read-once branching program, except that now we require each state of the program has in degree at most 2. So there can only be 2 edges arriving to these states. And in other words, the graph between 2 adjacent layers is a regular bipartite graph. So for example, both of these programs are computing the function n of x1 and x2 and x3. And you can see that the left-hand side, the program on the left-hand side is a regular program, but the program on the right-hand side is not, because the space we circle in red has 3 incoming edges, which has in degree 3. And so it's not regular. So while regular programs seem very restricted because of this regularity condition, it was shown that actually to de-randomize randomized log space, it suffices to just de-randomize poly n with regular programs. So a further restriction of read-once branching program is called the read-once permutation branching program. And this is just a regular branching program, but in addition, we further require that all the incoming edges to each stage has distinct edge label. So for example, both of these programs compute the function x1 and x2, and then take the O of x3. The first one is a regular program because each state has 2 incoming edges, but it's not a permutation program because the states in the states circled by red has both of these incoming edges labeled by the same label. So the first state, both edges are labeled blue, which corresponds to 1, and the second state is labeled by the black. The edges are labeled by black, which corresponds to 0. The program on the right-hand side, on the other hand, is a permutation branching program. So if we require all the 3 models to have the same width, then we can see that permutation programs are a subclass of regular programs, which are also a subclass of general branching programs. It's just because we are imposing more and more restrictions to the model. So recently, there's been some work which studies regular programs and permutation programs of unbounded width, and we will also talk about this in this talk. So now that I have defined what branching programs are, I can talk about our results. And here is our result. We saw that any function computable by a width W read-once regular branching program with S accept states in the final layer has its L1K bounded by the following quantities. The first bound we give is the width W times the acceptance probability of the function. And the second bound is the number of accept states multiplied by this quantity, n times log n divided by k, and the whole thing raised to the k minus 1 over 2. So now let me make some remarks. So for the first bound, note that for k equals to 1, which is the first level, this bound can be matched by the end function on w minus 1 bits, which we've seen earlier that it can be computed by with w permutation program. And this matches the bound we give because the end function, the Fourier coefficient of the end function has the same magnitude as the acceptance probability of the end function, which is just 2 to the minus w minus 1. And there are only w minus 1 coefficients on the first level of a function. In particular, the bound we give is improved on the previous bound by Reingold, Steichen, and Fadin. So we improve the dependence on W by quadratic factor. And more importantly, our bound has this acceptance probability factor, which is going to be important for our application. Okay. So for our second bound, note that this bound is independent of the width W. And in fact, at the first level, it is also independent of the length of the program, which is n. And this is the first non-trivial bound for unbounded width program. And moreover, we give an almost matching lower bound, showing that there is some functions computable by a permutation program with one accept stage, which has L1k roughly n over k to the k minus 1 over 2. So now let me talk about some applications of our theorem. Our first application is the coin problem. Let me define what it is. Let us use x sub delta to denote the distribution of NIID random coins, where each coin is equal to head with probability half plus delta. So the coin problem asks whether a class of functions can distinguish delta biased coins x sub delta from the unbiased coins x sub 0, which is essentially the uniform distribution. And we are interested in the distinguishing of advantage of this problem. This problem was actually implicitly studied by the earlier works by Aitai and Valiant, and where they want to understand the circuit complexity of computing the majority function. And later, Brody and Verbin, who introduced the term coin problem, studied this problem for pseudo-randomness against space-bounded computation. And recently, the coin problem was also studied by Braverman, Garg, and Woodruff, where they use these results on the coin problem to give streaming lower bound. So recently, it's known that the coin problem is almost equivalent to the L1 norm of a function at the first level. In particular, Avishai Tao showed that if the function class is closed under restrictions, which means that given a function in a class, if we restrict some of the input bits, then the restricted function still remains in the function class. Okay. And he showed that the distinguishing advantage of the coin problem for a function class that is closed under restrictions is bounded by the Fourier L1 norm of the function class at level 1 times roughly essentially the bias of the coin. So we call that in our second bound of the L1k, it is really just the number of accept states of the program. So we have the following corollary. So the takeaway message here is that unbounded width permutation programs with a single accept state cannot really distinguish delta bias coins from uniform, much better than just reading the first coin and output the answer. So our second result is on pseudorandom generators, PRGs. And this is a fundamental object in the study of pseudorandomness. So a pseudorandom generator for a class of functions is an algorithm that stretches a small seed of S bits to N bits so that every function in this class cannot distinguish a random output of the generator from the uniform random string. And here we give new explicit pseudorandom generators for unordered regular permutation programs. Which one's permutation programs in both the unbounded width and bounded width settings. So let me define what unordered means. So unlike an ordered program, which is just a program that reads its inputs in a fixed order fashion, for example, the program always reads the input in the order of x1, x2, then through xn. An unordered program gets to choose the order of the input bits any way it wants, as long as each bit is read at most once. So here you can think of the order is just a permutation of 1 to n, and which can depend on the input x. And it's been shown that the generators that work very well on ordered programs, such as the Distance generator and the INW generators, fail to work on unordered regular with one's branching programs. So because we just showed that permutation programs of unbounded width cannot really distinguish bias coin much better than just outputting the first coin, then we can just sample this bias coin approximately, and by doing that, we get an explicit PRG of non-trivial seed length 0.99n for unordered permutation program with a single accept state. And this is the first non-trivial explicit PRG for unordered unbounded width permutation program. And note that in the ordered case, we actually have much better seed lengths for unbounded width programs. And this work by Hauser, Pine, and Fadan, they actually show that random constructions of PRGs need to have seed length roughly n over 4. Now we move on to the bounded width case, and we are going to use the following result by Chattopadhyay et al. And they show that if a class of functions is closed under restrictions and their L1k is bounded by b to the k for every k, then we immediately get an explicit PRG for this function class with seed length roughly b squared times O tilde log n. And because we just proved that, bounded width program, for bounded width programs, their L1k is bounded by W, essentially W, so we get a PRG with seed length W squared times O tilde of log n. And this gives a slight improvement on the previous seed length, which is the width W to the 4th times O tilde log n. So our last application of our theorem is that we also get Fourier growth bands for more general classes of functions. So first I have to define what a disjoint composition of functions mean. Suppose we are given an outer function f and some inner functions g1 to gn. Then we can compute their disjoint composition as follows. First, we compute g1, g2 to gn on disjoint inputs x1 to xn, and then we just feed their outputs to the as inputs of f to compute the function. And we will use the following composition theorem by Brashok et al., where they show that if the outer function has L1k bounded by the acceptance probability times b to the k, and all the inner functions ti has their L1k bounded by the acceptance probabilities times c to the k, then their composition is L1k bounded by the acceptance probability of this composition function times b times c raised to the k. And because our L1k band has this acceptance probability in it, so we get new Fourier growth bands for compositions of Witt-One's permutation branching programs with other classes of functions, which also have this acceptance probability in their L1k band. So for example, we get Fourier growth bands on compositions of regular programs, permutation programs with, say, arbitrary Boolean functions, subclasses of low-degree polynomials, and decision trees. Okay. So now let me give some ideas behind the proof of our main theorem. So let me start with the case k equals to 1, which is the most important step. So we're going to show that the L11 of regular programs is bounded by the acceptance probability times W minus 1 or the number of accept states. So for a set of states in the final layer of the program, we're going to denote the program with this set of states as accept states to be B sub S. And we will show that L11 of the program is bounded by the size of S, which is the number of accept states in the program, times the rejection probability of the program. And this clearly implies the first band in the theorem, mainly because the L11 of the program and its complement is the same. So we can replace this set S by its complement and the rejection probability by the acceptance probability. And now note that the complement of S has size always bounded by W minus 1. So this gives our first band. So to prove the first band in the first level, we're going to prove the following lemma. And the proof goes by the following. We are going to do induction on the length of the program n. So the idea is the following. If we consider S our accept states in the final layer, we can consider two sets of states in the previous layer. And we let T here to be the states with both of these the outgoing edges going into the set S, and we let T sub 1 to be the states with exactly one of the outgoing edges going into S. And we can express the L11 of B sub S in terms of the L11 of the two programs B sub T and B sub T1. And and note that by regularity, the size of S is exactly equal to the size of T plus the size of T1 divided by 2. And this is where regularity comes in our lemma. And once you have this observation, then the rest is just a simple calculation. But let me also give some intuition of this inductive hypothesis. So note that when T1 is empty, then there's nothing to do because S accept state is really just an S. Now, if T1 is non-empty, then actually we have fewer accept states in the final layer than the previous layer. But note that because of this half here in the acceptance probability, so the overall acceptance probability of the program becomes smaller, which is sort of explains why the rejection probability appears in the hypothesis. Okay, so let me quickly mention how to handle general K. So we are going to apply induction on K, which is essentially just the same inductive argument appears in previous works. And note that in these arguments, we require a step which is called the local monotonization of the program. And because permutation programs are not closed under monotonization, it is crucial for a first level bound that it holds for the wider class of regular programs. And our second bound is actually a bit more involved. It requires combining some other ideas in previous works. For example, we have to use the level K inequality for arbitrary Boolean functions. And we also need to use the recent work which shows how to approximate unbounded width program using a program with bounded width. Okay, so that's all I wanted to talk about the proof. So let me end the talk with some quick open questions. So the first question is that we obtain the first non-trivial explicit PRGs for unordered unbounded width permutation programs, but the seed length is pretty bad. It's at seed length 0.n. So the question is whether it is possible to construct a PRG with, say, polylog n seed length for this model. And the second question is about unordered bounded with regular programs. Can we get a better PRG using regularity than general branching programs? And currently, we don't know any better PRGs using regularity. And the challenge here is that because regular programs are not closed under restrictions, and this is the reason why most of our applications only apply to permutation programs. And finally, we believe our L1K bound for unbounded width programs should be S times n over K raised to the K minus 1 over 2. So that is, we think that this log n shouldn't appear in the right bound. But we don't know how to remove this log n factor in our result. So it would be great if this can be removed to match our lower bound. Okay, so this is the end of my talk. Thank you for listening.